All right, good morning, everyone. Welcome to NASA's Johnson Space Center. So nice to be meeting with you guys today. My name is Michael Hare, and I'm an education specialist here at the Johnson Space Center. Now, we're going to have a great program today, learning all about the planet Mars, what it actually takes to get NASA spacecraft all the way to the red planet, and how we're actually working on missions right now to actually do that. So you guys ready to get started? Let me see a big thumbs up. All right, excellent. So here we go. All right, good morning, everyone, and welcome to the Johnson Space Center. Once again, my name is Michael, and I'm going to be your host today as we talk about what it actually takes to get missions to Mars. Now, I'm coming to you live all the way down in Houston, Texas, at NASA's Johnson Space Center. Now, can anyone raise their hand and tell me, what do we actually do here at the Johnson Space Center that may be different than the other NASA centers? Anybody know?
They train astronauts.
Right. We have many different training facilities where we actually train them before they actually go up into space. So before we start talking about Mars, I thought you guys would like to see where we actually train the astronauts. Now, it is a Saturday, so there's not a lot of activity going on. For example, in this facility right here, this is called the Neutral Buoyancy Lab. It's one of the largest indoor swimming pools in the world. Now, why do you think we dunk astronauts in a big swimming pool? Anybody have any ideas?
To simulate the effect of when you're out in space.
So they don't sink to the bottom or float up to the top, and that way we can simulate that microgravity environment. Now, this pool is so large that we can put huge modules of the International Space Station underneath the water. It's about 40 feet deep and holds about 6.2 million gallons of water. But that's big enough to train our astronauts for going into space. Now, that's not the only building we have here. Here's the actual building that I'm coming to you live from. This is called the Space Vehicle Mock-Up Facility. And here we have huge trainers of the space station. You can see the space shuttle orbiter way in the background. And we're moving new vehicles in, like the Orion Command Module. So we can train future astronauts, maybe yourselves, on leaving low Earth orbit and journeying out into the solar system, maybe to the moon or to Mars. So we've actually got some awesome trainers right here inside this building where the astronauts can go inside and learn how everything works before they actually go up into space. Now, we're also home to Mission Control, and we actually have the control center right here on site, Building 30. And let me show you a live view. Here's a live view inside the International Space Station control room. As you can see, it's minimally staffed on the weekends because the astronauts and cosmonauts actually get some time off over the weekends. They're led by a flight director, and they've got all the different console positions right here in Mission Control, from the air that the astronauts breathe to the electrical power they use to run everything. Even the thruster control is done right here in Mission Control. Now they can also control it up on the space station as well, but we have really smart, dedicated people right here in Mission Control to make sure the mission goes smoothly and that the crews are healthy while they're up in space. Now, does anyone know how many people are actually up in space right now?
3, 5, keep going. 4, 10. 4, 12, 10. They're all over.
You're actually in a good ballpark. Awesome. We actually have 6 people in space right now. We've got 3 Russians, 2 American astronauts, and 1 Japanese astronaut living and working on board the space station right now. And we actually have some live views from space, so I thought I'd show them to you right now. Over on the right is the space station. We got some laboratory modules. We got a platform that they use to stow items when they do a spacewalk. We even have a little antenna over on the left that you can see that helps communicate down with the ground. And look at the beautiful Earth moving by. We've got lots of ocean, lots of clouds in the picture. Let me see if we've got another view. Oh, there we go. There's a nice wide shot. Sometimes we actually take some of the bandwidth away from some of the channels in order to send scientific data down. And that's why it looks like the Earth is jittering by in the distance. It doesn't have 30 frames per second like we're normally used to seeing on normal video. But look at that big module in the foreground. That is a Japanese cargo carrier called the HTV. Oh, and we just lost downlink. And that's bringing lots of supplies up to the space station. Now we use the robot arm to grab it and put it down where we want it to dock it. And then we can open the hatches and the astronauts and cosmonauts can get all those awesome supplies that they need to live and work up in space. All right, now today we're going to be talking about Mars and what it actually takes to get to Mars. And hopefully your generation will be the astronauts, engineers, and scientists that will actually get to travel there. Now, how far have humans actually traveled? How far have we actually gone into space? Anybody know? Who knows?
Does anyone think we've gone outside of the galaxy?
But guess what? Humans have only gone about 250,000 miles away from Earth. That's as far as we've gone. Anybody remember the Apollo missions? We had 6 separate missions. 12 men walked on the surface of the moon. That's as far as humans have ever gone, is just to our natural satellite, the moon, which is on average about 243,000 miles away. It's the furthest about 250,000 miles away. So that's it. That's as far as we've ever gone. But that was an incredible journey, an amazing place, very different than our home Earth. And I wanted to show you what it was like to actually walk on the surface of the moon.
Jack, you read me? Yeah. Hello, Houston. 17, loud and clear. We'd like you to leave immediately. If not sooner.
Kind of an interesting way to move around on the surface. Does anybody know why he's hopping like that?
Low gravity.
Very good. Yes. The moon is much smaller than the Earth, about 1/4 the size, so it has less mass and less gravity. Very good. It's about 1/6 that of Earth's gravity. So if you were to take your weight and divide it by 6, that's how much you'd weigh on the moon. So it's really easy to move around. A little bit tough to move around in that pressurized suit, but as you can see, they actually more hop on the surface of the moon. Now today, we're going to be talking about Mars and what it's actually going to take to get to the red planet. Now, does anybody know what the gravity is like on Mars? Is it more, the same, or less than the Earth?
Less.
All right. Yes, the less wins. Actually, great. Good job. It's about 1/3 that of Earth's gravity. So we're going to have to deal with those similar situations when you future astronauts actually get to Mars. Now, we've always been fascinated with Mars ever since we built the first telescopes to look beyond our Earth sky and see what is out there. Now, we've been fascinated by the red planet because it's so close compared to some of the other planets in the solar system. And some brilliant scientists and astronomers, for example, like Giovanni Schiaparelli, actually took detailed notes on what he saw looking through a telescope at Mars. And what he saw actually created a lot of controversy in his time, because he saw little canals, or what he thought might be roads, on the surface of Mars. Now, what did this mean? Is there water on Mars? Were there a civilization building roads on Mars? They weren't sure at the time, because they had just rudimentary telescopes at the time, so they didn't have the technology to really get a close-up look of the red planet. Now, this sparked a lot of people's imagination and curiosity about what might be on Mars, and many different writers throughout our history created amazing stories about what might be on the planet Mars. Now, did anybody see the most recent War of the Worlds film? Let me see a show of hands. With Tom Cruise? Maybe a couple people? That movie was about how Martians actually came from Mars to try to conquer Earth, and what we did to actually stop them. H.G. Wells wrote the first story about War of the Worlds, and it was an amazing story. Like I said, a lot of curiosity about what Mars is all about. In fact, Ray Bradbury did a whole Martian Chronicles about what it would be like to actually colonize Mars, and how those people would be different than the people back on Earth. So a lot of amazing stories. In fact, even made it into a popular culture too. For example, cartoons have been made about Martians and what it's like on Mars, and also feature films have been made about what it's like to journey to the red planet. Now, you guys actually get to do science fact. You guys actually get to travel there, and one of the things that's going to help you out is all of the years and years of data that we've gathered from previous missions going to the Martian surface. Now, we've been sending things to Mars since the mid-1970s. In fact, one of the first missions was our Viking lander to actually land on the surface of Mars. And it took some amazing pictures. For example, in the left picture, what do you think that looks like in the left side of the picture, the black and white one?
George Washington. Hey.
This created a lot of controversy as well. We were wondering, wait a minute, was there a civilization that lived there before, and this is just an unburied remnant of someone buried on the surface? Actually, this is a much larger view than just the size of a human. In fact, it's a huge mountain range, and but we didn't know, because this was the best image we could take from the early spacecraft that went to Mars. In fact, now we know that it's a much more detailed mountain terrain, and it wasn't until 21 years later when the Mars Global Surveyor was able to take this picture of that same mountain range that looked like a face on Mars. So as you can see, over the years, we're sending more and more technology to Mars and learning more about the Martian surface. Now, Mars is an amazing place. Now, does anybody know how large Mars is? What do you think? Is it bigger than the Earth, the same size, or smaller?
Smaller?
All right, it is smaller. And guess what? You're right. It's about half the size of the Earth. But even though it's half the size, it's got some incredible features on it. And I'll show you some of those features in just a little bit. But first, I wanted to talk about what are some of the differences and similarities of the Earth and of Mars. For example, let's just look at the physical properties. For the Earth, how long does it take Earth to rotate one time on its axis? All right, it's already 4 hours. Now, does Mars rotate?
Yes.
All right.
24 hours? 3 days?
It's very similar to the Earth's rotation. So the days are going to be about the same. So it'll give us the same amount of sunlight. So we'll have that much time to do tasks on the surface. So that's very important to know what the differences and similarities are between Earth and Mars. Now, what about period of rotation? How long does it take Earth to, revolution? Period of revolution. How long does it take Earth to revolve one time around the sun?
1 year, yep.
5 Earth. Now, Earth is about an average 93 million miles away from the sun. Mars is about 142 million miles away from the sun. So it's actually going to take Mars a lot longer to make that journey all the way around the sun. In fact, it takes about 687 Earth days for Mars to go all the way around the sun. Now, what about natural satellites? How many natural satellites does Earth have? Very large object, has a big effect on lots of things down on the planet. Everything, there's a nice little tug of war going on between the gravitational forces of both the Earth and the Moon, and also that orbiting around the Sun. Now, Mars also has moons. It actually has 2 moons. The first one is called Phobos. As you can see, it looks a lot different than our moon, doesn't it? A lot more impact craters, a lot more irregularly shaped. Look at this large one right here. Huge impacts. In fact, many NASA scientists believe that Phobos and Deimos are captured asteroids from the asteroid belt, maybe left around from the early collisions that happened in the early formation of the solar system. Now, this is Phobos, and this is Deimos. Look at Deimos' shape. This one is very irregularly shaped. Looks more like a lima bean than it does a nice round sphere like many of the planets actually look, or our moon. So as you can see, 2 different objects orbiting around the Martian surface. Now remember how I mentioned different geological features? We have lots of amazing features right here on Earth. For example, what's the largest mountain range on the Earth? Anybody know?
Mount Everest, Himalayas.
Yeah, Mount Everest is about 29,000 feet, about 6 miles high. But actually, did you know that there's actually something on Mars that's 3 times larger than this actual mountain right here? There's actually a volcano on Mars called Olympus Mons that is 16 miles high. Very, very amazing feature on the Martian surface. In fact, if you were to take this overlay and put it over some of the states in the United States, it would be the size of Arizona. So amazing features on the Martian surface. Now there's also, we actually have some amazing volcanoes on our Earth. For example, here are the Hawaiian Islands. And of course, the large island of Hawaii actually has an active volcano. But volcanoes form a little bit differently on the surface of Mars than they do on the Earth itself. Now, Olympus Mons is 3 times larger than Mount Everest. How do you think a planet half the size of Earth can get huge features that are bigger than the things on Earth? Does anybody have any ideas? Maybe how that volcano can get bigger than anything on our Earth?
Lower gravity, would you say? Nothing to keep it down?
Okay. Also, we have plates that shift constantly around our Earth. It causes earthquakes, and when 2 plates hit each other, they actually push the land upwards, creating mountain ranges and sometimes volcanoes as well. Now on Mars, things happen a little bit differently. Earth, we have that plate motion, and sometimes it can form over a long, long period of time many different mountain ranges like you're seeing right here. Now on Mars, they don't have plate motion. So if a volcano spews out stuff from the core, it actually just falls out over it, builds, and then cools, hardens, and the more volcanic material that comes out actually just builds on top of itself. So that's why Olympus Mons is so much larger than the volcanoes or the mountains that we actually have here right on Earth. All right, now we also have huge valley systems. For example, does anybody recognize this valley system right here?
Grand Canyon.
Grand Canyon's about 277 miles of river going right through it. From rim to rim, it's about 10 miles, and average depth is about 1 mile. But once again, this is just very tiny in comparison to some features on Mars. There is a valley system called Valles Marineris that is much, much larger than the Grand Canyon. The length is about 2,500 miles across. So that'd be the size of the United States from California all the way to New York. It has about 310 miles wide and 5 miles deep. So even though we think the Grand Canyon is very, very large, it pales in comparison to features on Mars. So we want to learn all we can about Mars before we actually send astronauts just like yourselves to Mars. So what we're doing is actually sending spacecraft there. We've sent landers, orbiters to go around. We've even done flybys of the planet. And we're surveying the surface to see what it is like. Now, it's very difficult to actually get to Mars. And how are we actually going to do that? Well, I've got a little video here that shows how we're actually going to try to get spacecraft and how we've done it in the past to Mars itself. So let's take a look.
How do you get to Mars? If you want to send a spacecraft all the way to Mars, first you'll need a fast rocket to escape the pull of Earth's gravity. The heavier your spacecraft, the more powerful your rocket needs to be to lift off. Next, make sure you launch at the right time. Mars and Earth orbit the Sun at different speeds and distances. Sometimes they're really far apart, and other times they come closer together. About every 2 years, the two planets are in perfect positions to get to Mars with the least amount of rocket fuel. That's important. The total trip is over 300 million miles. Finally, make sure your aim is right. You can't shoot for where Mars is at launch time. You have to aim for where it will be when you get there. It's a lot like how a quarterback passes a football. Also, you may need a few thrusts to correct your direction along the way so you don't miss Mars. If all goes well, you'll get to the red planet in about 7 or 8 months. Then, if you actually want to land on Mars, well, that's a whole other challenge.
All right, and that's exactly what the Mars Science Laboratory mission is all about. Curiosity, our largest rover yet, is on its way to Mars right now, and hopefully late Sunday night Pacific time, early Monday morning Central time, Curiosity will be landing on the surface of Mars at Gale Crater to see exactly what is there. Now, it is very, very difficult to actually land a spacecraft on Mars. We've done several different ways of actually landing a spacecraft on there. And I wanted to show you another video on how hard it actually is to get a spacecraft and land it on the surface of another planet, millions and millions of miles away from the Earth itself. So let's take a look on how hard it is to land.
How hard is it to land Curiosity on Mars? On a scale from 1 to 10, landing on Mars is a 20. Curiosity is the biggest, most capable Mars rover yet, and needs a new type of landing to reach the ground safely. In this 7-minute trip to the surface of Mars, we have to slow down from over 13,000 miles an hour down to 0. Hundreds of things have to go just right. Curiosity must hit the atmosphere at just the right angle, endure extreme heat from friction as it descends through the atmosphere, open its parachute at just the right time, use radar to know exactly how high it is, free itself from the parachute, perfectly fire 8 rocket engines to slow final descent, drop down dangling on 4 cables, lock its wheels into place just before landing, and cut the cables right at the moment of touchdown. And even if we do everything right, Mars can always surprise us. It's a big challenge, but a big opportunity to help unlock the mysteries of Mars.
Isn't that amazing? So that's actually what we're working on to actually land the Curiosity rover on Mars. Now, it's difficult to actually give all the commands to the actual spacecraft and rover in that sequence that is going to land on the ground. Because think about it. On average, Mars is about between 36 and 49 million miles away from the Earth. So just signals, sending out communications or data to the spacecraft takes several minutes to actually get there. For example, just a call may take 12.5 minutes to actually get all the way to Mars. Something else can take its place, like they have many different retro rockets on the upper stage to help it lower slowly down. For example, let's say one got stuck or one was firing too much. Others can compensate to try to help out in that situation. But there are lots of things that have to happen automatically in order for a spacecraft to land. And if something does go wrong, it might cause a failure of the mission itself. Like we've had many different missions go to Mars, and not all of them have been successful. But we try to think about all the contingencies, everything that could possibly happen, and try to counteract those or make backup systems that can take over if something fails. Good question. sending spacecraft to Mars for many, many years, since the mid-1970s. In fact, we've had many different rovers on the surface as well. As part of the Mars Pathfinder mission, Sojourner, a very tiny spacecraft, actually traversed the surface of Mars. Of course, you guys have been hearing in the news all about Spirit and Opportunity. For the last 7 years, they have been on the surface of Mars, driving around, taking amazing imagery of the surface, drilling into rocks, learning about what they're made of, and hopefully finding future sites for you future astronauts to land on the surface of Mars. So both of those have been very, very successful. One of them actually is stuck and is no longer moving around on the surface, but it's still sending back data and getting pictures of the area. So we're actually got some amazing missions. And right now, we're sending another one there right now. Now, it's called Curiosity. As you can see, it's much larger than any other rover we've sent in the past. It's actually the size of a small compact car. And it's an amazing vehicle. Now, we have to use a different way to actually get this vehicle down on the surface because it's so large. So we're going to use this amazing sky crane system with an upper stage with rockets to actually slow it down. And it's actually going to land the rover on the surface, then cut those bridles and zoom off away from the Mars surface. Now, I do actually have another video that I wanted to show. Well, this is a little bit longer video. It shows you all about entry, descent, and landing. That time when the spacecraft has to come through the atmosphere, open the heat shield, and actually use that sky crane to land the vehicle on the ground. So here we go.
When people look at it, it looks crazy. That's a very natural thing. Sometimes when we look at it, it looks crazy. It is the result of reasoned engineering thought, but it still looks crazy. From the top of the atmosphere down to the surface, it takes us 7 minutes. It takes 14 minutes or so for the signal from the spacecraft to make it to Earth. That's how far Mars is away from us. So when we first get word that we've touched the top of the atmosphere, the vehicle has been alive or dead on the surface for at least 7 minutes.
Entry, descent, and landing, also known as EDL, is referred to as the 7 minutes of terror, because we've got literally 7 minutes to get from the top of the atmosphere to the surface of Mars, going from 13,000 miles an hour to 0 in perfect sequence, perfect choreography, perfect timing, and the computer has to do it all by itself with no help from the ground. If any one thing doesn't work just right, it's game over.
We slam into the atmosphere and develop so much aerodynamic drag. Our heat shield, it heats up and it glows like the surface of the sun. 1,600 degrees.
During entry, the vehicle is not only slowing down violently through the atmosphere, but also we are guiding it like an airplane to be able to land in a very narrow, constrained space. This is one of the biggest challenges that we're facing, and one that we had never attempted on Mars.
Mars is actually really hard to slow down because it has just enough atmosphere that you have to deal with it. Otherwise, it will destroy your spacecraft. On the other hand, it doesn't have enough atmosphere to finish the job. We're still going about 1,000 miles an hour. So at that point, we use a parachute.
The parachute is the largest and strongest supersonic parachute that we've ever built to date. It has to be able to withstand 65,000 pounds of force, even though the parachute itself only weighs about 100 pounds.
When it opens up that fast, it's a neck-snapping 9 Gs.
At that point, we have to get that heat shield off. It's like a big lens cap blocking our view of the ground to the radar. The radar has to take just the right altitude and velocity measurements at just the right time or the rest of the landing sequence won't work.
This big, huge parachute that we've got, it'll only slow us down to about 200 miles an hour. And that's not slow enough to land. So we have no choice, but we've got to cut it off and then come down in rockets. Once we turn those rocket motors on, if we don't do something, we're just going to smack right back into the parachute. So the first thing we do is make this really radical divert maneuver. We fly off to the side.
Diverting away from the parachute, killing our horizontal velocity and our vertical velocity, getting the rover moving straight up and down so it can look at the surface with its radar and see where we're going to land. And we head straight down to the bottom of a crater, right beside a 6-kilometer high mountain.
We can't get those rocket engines too close to the ground, because if we were to descend propulsively with our engines all the way to the ground, we would essentially create this massive dust cloud. That dust cloud could then go and land on the rover. It could damage mechanisms and it could damage instruments. So the way we solve that problem is by using the sky crane maneuver.
20 meters above the surface, we have to lower the rover below us on a tether that's 21 feet long, and then gently deposit it on its wheels on the surface.
As the rover touches down and is now on the ground, the descent stage, it's in a collision course with the rover. We must cut the bridle immediately and fly the descent stage to a safe distance from the rover.
All right, so that's the exciting sequence of entry, descent, and landing. How we're going to get Curiosity down on the surface of Mars. Now, we're really excited. The scientists at the Jet Propulsion Laboratory are working right now, practically around the clock, monitoring the systems of the vehicle. Once again, it's going to land at Gale Crater. As you can see, the yellow oval is the landing ellipse where the vehicle is actually going to land. And it's going to be right near Mount Sharp. That's going to study for about 2 years on the surface of Mars. All right, now those were all the videos that I wanted to show you today. There is one final thing. Do we have any techies in the audience? Anybody loves technology, works a lot with computers? Let me see some hands. All right, excellent. Well, I've got an amazing program for you that you guys need to check out. And I'm pulling it up right now. I'm going to show it to you. It's called Eyes on the Solar System. And let's see, here is the address. It's eyes.nasa.gov/server/index.html. And this is an amazing program where you can do some 3D visualization of the Mars mission and of the solar system itself. Now, that's the main feature going on right now here on the main website because, of course, Curiosity is going to land in about 41 hours from now on the surface of Mars. So you can actually click here and download a little Java applet, and it'll allow you to visualize what it's going to be like to land that rover. And right now, I pulled up this screen right here. Let me get rid of that thing right there. Right now, the Mars Science Laboratory in Curiosity is about 325,000 miles away from Mars. It's traveling at a velocity of 8,000 miles per hour, and it's going to touch down in about 39 hours, 48 minutes. So the next stage is the cruise stage separation. And if you'd actually like to preview the whole process that we saw in that video of how this vehicle is going to actually land, you can go over here to preview mode and preview that landing. One of the great things about this visualization tool is you have total control. I can move my little mouse by clicking and dragging, and I can go all the way around this vehicle, see all the different parts from the upper stage right here, all the way over to the heat shield. I can zoom in, and I can zoom out. I can even go to different locations. I can go back to Earth. I can go to Uranus. I can, of course, go to Mars as well. And let me go ahead and click on preview mode so I can show you the amazing things that it can actually do. It's loading the material right now. It's going through a preview mode. Basically, I can rotate it, and everybody can see Mars right there. There you go. Now it's coming into Mars. It's about 2,500 miles away. And one of the great things about this interface down below that I'm highlighting is there's one called date and time. And you can take it and move forward in time to show the different sequences. Now, I wanted to show you the cruise stage separation in about 3 seconds. Watch what happens in 1 second. There you go. You can see different parts of this mission where the stage comes out, and you can rotate in real time as you're doing it. So this is an incredible program that you can actually see all the different stages of the mission. So let me forward to the next one where they stop spinning. Despin in 20 seconds. There you go. Now it starts to control itself using thrusters. Now it's also going to give out these little weight balances that's helping it keep its angle as it enters the atmosphere. And that's going to happen in 48 seconds. Let's speed it up again. Okay, it's starting to jettison some of them. You can try to see where they are. I see it's one that's going off. It's going to smash into Mars. Now the entry interface point when they enter the atmosphere is in about 7 minutes. So let's zoom in, or let's speed up, sorry. There we go. Now we're entering the atmosphere. And look, you can still do 3D as well on this one as well. Look at that. You can go all the way around. See how it's entering the atmosphere? How it gets hotter and hotter as it's coming in. There we go. Now we're really into the atmosphere. If you want to rotate, you can actually look at Mars. You can actually see the surface. Off in the distance is the landing site. So we're coming through the atmosphere right now. And like I said, you can go all the way through the entire phase of the mission. I won't spoil it for you. I'll let you guys do it on your own. But this is an amazing tool. Once again, let's see. Here is the website. It's https://eyes.nasa.gov/server/index.html. And it's an amazing simulation. I'm going to be watching this tomorrow night into Monday morning as I'm following the mission and watching NASA television as well. And just to let you know, NASA TV is covering this flight, and it's actually going to be having live television. Maybe you might not see pictures of Mars that first day, but you're going to see the control room. You're going to get to talk to the experts. They're going to be giving commentary. So it's going to be really exciting following this mission of Curiosity's landing on the surface of Mars. All right, now that's all I had for you guys today. And it's going to launch the Orion command module into space. And hopefully we'll leave low Earth orbit with this vehicle, maybe journey to an asteroid or even go on to Mars. So yes, we are working on the rockets to actually get humans that far.
This one's mine. What do you think about privatization? Do you think that's good or bad?
Oh, I think it's excellent. Anything to explore beyond low Earth orbit or get out into space to learn more is definitely beneficial for everyone here on the planet. Think about all the technology advancements that have come out of going into space. Does everybody love having their iPhones and their iPads and being able to communicate anywhere in the world? Well, that wouldn't have been possible if we didn't send things into space. There are satellites orbiting around the Earth, bouncing those signals all over the globe. And that's a direct benefit from the space program. So I definitely think whatever opportunity we can to get into space, whether it be just a government program or a private program, I'm all for it.
Last question.
Okay.
Do you think we'll ever be going to
Are we going to go to Europa?
Good job. Yeah, actually I do. Hopefully it'll be robots first. Europa is an amazing moon of Jupiter, and below its icy surface may exist liquid oceans or water. So we're going to send robots first because think about it. Jupiter is really far away. On average, it's about 483 million miles away from the sun. So it's really super far away from us. So we're just going to take in baby steps. We've been in low Earth orbit for a long time. We've been to the moon. Now we're going to go to Mars. Maybe we'll go to those outer planets in generations from now.